Howdy, howdy. This is section, which I didn't even write down, 2.5, the graph of y equals kx squared. It should be amazing and exciting in every way. There is your journal choice. You can submit it on Edmodo or on paper if you would like. Okay, objective and what's the point? Here's what's going on today. We are going to extend the idea of slope from section 2.4 as that rate of change that we started to talk about. But now we're going to talk about it in regards to nonlinear graphs. This is really, really important because every graph that you could have has a rate of change, and it's related to, but it is different than slope. And today I think you're really going to understand what I mean by that better. Okay, these are the four, standards the book wants us to address that we're going to do today. We're going to do all these things in your homework. And the reason that we want to talk about this so much is because not all relationships are linear. In fact, most of them I would almost say are not. And we need to familiarize ourselves with as many data trends as possible. And this is one that shows up a lot, especially in science. Okay, so I think this is a lot of worthwhile reasons behind learning it. Okay. Remember from 2.4, rates of change in y equals kx all return the same value. It's the slope. It is that constant k, because we figured out that k and m are the same thing when we're talking about direct variation of this sort. Y equals kx is the same thing as y equals mx. And the reason this k value, this slope, this rate of change comes up the same every time is because slope is the change in y and the change of x. It's constant. These steps will always be the same height to width ratio, okay, because that is a constant slope. The steepness of that line doesn't change because we talked about slope as the steepness of a line, and it is always the same, okay? Now, this will be different when we talk about the graph of y equals kx squared. You still need 2 points to find the rate of change, but whenever you pick two different points, it will give you back different values, and that's going to be expected, because if you notice, if I picked these 2 points, that's going to be a steeper rate of change than if I picked these 2 points. Okay, on this graph over here, it wouldn't matter which 2 points I pick. That line that I would draw between them is the same, but here it will really depend on what 2 points I pick. Okay, when you get multiple rates of change between points, then it automatically we know it's not a line. We don't know exactly what it is. You don't know necessarily that's a parabola. We'll talk about other rates of change later this year, but it's definitely not a line. Okay, so that's what we're talking about today. And here's your hint. When you find slope or rate of change, make sure you use ordered pairs. The process of finding slope and any rate of change is the exact same. You find 2 ordered pairs, and then you use your formula, which you guys call it the slope formula. I almost wish they would call it the rate of change formula when they teach this to you. y2 minus y1 over x2 minus x1. The process is the same. The difference is, on lines, you'll only get one answer, no matter what points you pick. On anything else, you'll get lots of answers for your rate of change, depending on what points you pick. Okay, the one thing I'm going to tell you to be careful with, because I think it might show up on your homework, check the scale on the axes whenever you get your ordered pairs. Make sure that you're not just assuming that the scale is 1. Sometimes it could go by 5s or 10s or 2s, whatever. So pay attention to that. Okay. Practice with rates of change. In example 1A on your book, and it says it's on page 101, they're giving you an example of a graph that has braking distance, graph with speed, and this is the formula. Distance is 1 over 20 s squared. Okay, this is your form, y equals kx squared. It is definitely direct variation because it's in that form. Okay, but we're going to talk about some of the rates of change. And if you would look on page 100, it will help when you're doing this. The first points they want to know for rate of change is between 10.5 and 20.20. Now if you look, 10.5 on your graph is towards the bottom, very close to the origin, and 20.20 is a little bit up from that. It doesn't look that steep, okay? You do this just like slope, and here is your answer. The answer is going to be 1.5 feet per miles per hour, okay? And that's what it means. Now we're going to talk about that in 1 second, so in case you have it, there you go. But let's go ahead and do the work. Okay, This is x1, y1, x2, y2. Okay? So as a habit, I do put m. I need to keep in mind that does not necessarily mean slope. It means the rate of change or the slope between those 2 points, the steepness between those 2 points. But I can remember this is different than slope because it's not going to be the same thing each time. So if you want to do rate of change, if you want to write it down, rate, I don't know, you could call it the rock. That's cool. Rock of change. No, I don't know. That's not really cool probably. But we're going to go ahead and do this. 20 minus 5 over 20 minus 10. Okay, 20 minus 5 is 15 over 10. Now, some of you guys will be like, Mrs. Bruno, you're such a hypocrite. You just told us not to use decimals, to use improper fractions. Okay, you could do that if you wanted to, 3 over 2. I want to explain to you what this means and then why I did use the decimal here. The y value is distance. The y was on bottom. So this is your distance. Oh, it's not. The y was on top. This is your distance. And the x value is s, and that was your speed. Distance and speed. Then I go back to my graph and I look. We're talking about feet per miles per hour. So feet is on top, miles per hour is on bottom. Okay? What is this telling me? That tells me that for every between these 2 points, between the points from going 10 miles per hour to 20 miles per hour, I need 3 feet to stop for every 2 miles per hour. We don't usually talk that way. So what I did was I changed it to 1.5 because then I can put it over 1. And then I could say from the rates from 10 miles per hour to 20 miles per hour, I need 1.5 feet for every increase of 1 mile per hour. That's what it means in terms of the graph. That is very important. Okay? You have to disclaim it because this is only the rate of change from 10 miles per hour to 20 miles per hour. You're going to get a different thing down here when we do this next one. Okay? But when you're figuring out what it means in terms of breaking distance, say what was that y value representing, because that was change in y. What was that x value representing? Look at your graph, figure out what was on the y-axis, what was on the x-axis, fill it in, distance, speed, go ahead to the units, feet, miles per hour. Okay, and again, we don't usually look at it this way, so we simplified it to over 1. Alright, so let's look at a different one. I think I can press this button. Oh my god, that's not what I wanted to happen. I just erase it. Okay, the next one. We're now looking at the rate of change from 2020 to 5125. Now you can tell if you look at the graph, this is representing a much steeper portion. Okay, here's the answer if you want to see if you know what you're doing. Okay, now I'm going to go ahead and work it. Okay, change in y over change in x, that's your rate of change formula. So now I have 125 minus 20. It's got x1, y1, x2, y2 over 50 minus 20. That gives me 105 over 30. Okay, and again, I'm going to go ahead and reduce that to a decimal this time because it does work out nicer when you're talking about rate of change to know what happens for 1 unit of measurement. And we get 3.5 over 1. Remember, the y value was representing feet. The x value was representing miles per hour. So what does this tell us in context? That's saying if you're going from the speeds 20 miles per hour to 50 miles per hour, it will take us 3.5 feet to stop for every 1 miles per hour change. That should make sense to you. If you're going faster, it's going to take you on average more feet to stop per speed. Okay? But it's a different value than we got from those first ones. So it is imperative that you give that disclaimer from 20 to 50. Okay? And we already wrote that down right there. Alright? So let's go on here. Here are words you need to know. A parabola, I think you guys know this, is a U-shaped graph, and we use it for the family y equals kx squared. Okay? Basically, if there's an x squared involved, you're dealing with a parabola, a U-shaped graph. They're so cute. This is a parabola. It has to be this way, or it could be this way. A sideways U is no good because these are going to be functions. Okay, the vertex is the maximum or minimum point on a parabola. So in this case, it's a maximum because it's the very top, and on this case, it's a minimum. It also marks the folding point because parabolas have symmetry. So I could fold this and they would match up. That was a really good drawing by me, actually. I'm really proud of my parabola because it looks symmetric. And for the graphs you're going to do at tonight's homework, if it looks just like y equals kx squared, the vertex is always going to be at the origin, which is 0, 0. Okay, they are reflection symmetric. You should have talked about this in geometry. They have a fold line, which helps when we graph. So the good thing about it is if you know that you have the vertex here at 0, 0, and you're only graphing this point, you could use symmetry to get this things in the third quadrant. And in all of our examples today, that fold line, that line of symmetry, is always going to be the y-axis. The reason that's always going to be the y-axis is because the vertex on all of these is 0, 0. So that is exactly where that fold line would happen at. Okay. We are going to do an activity in class, hopefully tomorrow, that we'll have explored the graph of y equals kx squared by plugging in different things of k. These are the things you should get from that, and I would include them in my notes. The ones that are of super importance to me are these two. They don't always come naturally to kids. 1k is automatically on a graph, and negative 1k is also on the graph. And that's what I'm going to use right now on this next example. Okay, we are going to sketch this without using a graphing calculator. Okay, you will find some things from doing the activity, such as if it is a positive number, we are looking at a graph that looks like this, not this way. We're going to have a smiling graph, not a frowning graph, because it is positive. Positive people are usually smiling. So we're going to graph this first one here, y equals 2x squared. Automatically, I know the vertex is at 0, 0. I also know that the fold line is coming right down here on the y-axis. Okay, so I need a couple points. Well, the point that I'm automatically going to do is that point 1k. 1 is here. What is k? 2. So 1, 2 is automatically on the graph. Well, I also know that this is a fold line, line of symmetry, so the point negative 1, 2 has to be on the graph. I know it's a U-shaped graph. That's really kind of enough for me. 3 points. Usually a lot of teachers will tell you 5 points, but if it says to sketch it without using graphing calculator, that's fine. If you wanted to plug in 2, then you would have to plug in 2 times 2 squared. That's 2, 4, 8. But I don't want my graph to go up that high. Okay? How about the graph y equals negative 2x squared? Well, this has a negative k value, so we're talking about a frowny face graph. So now we're looking at a graph that looks more like this one. Still has it 0, 0, but this time 1k will be 1. What is my k value? Negative 2 over 1, down 2. Fold line right here. Loop-de-loop. Okay, that's so nice. Oh, that wasn't as good, but it's okay. All right, I think that's it. I gave you a nice gift of math today. I hope you enjoyed it. Ta-ta.